Hey students, in this video we start our new series of organic chemistry. Okay, in this series we discuss about organic chemistry from basic to advanced level. Now what is organic chemistry? Organic chemistry is branch of chemistry which deals with organic compounds. Okay, now what are organic compounds? Organic compounds are the compounds containing carbon, hydrogen and oxygen. Okay, now in old times scientists believe that organic compound can only synthesize by nature. They believe that organic compounds cannot synthesize in lab, okay? But in 1828, the scientist Frederick Waller performed an experiment. He synthesized an organic compound by inorganic compound. He synthesized an organic compound, and the compound was ammonium cyanide, and he formed urea. Okay, now this is how our organic chemistry began, right? Now we see here our most important element of organic chemistry is carbon, right? So let's discuss some important things of carbon. Carbon has atomic number 6, all right? And electronic configuration of carbon is 1s2, 2s2, and 2p2, right? Now we see that the valence electron of carbon are 4, right? So carbon have 4 valence electrons. So to attain noble gas configuration, rather carbon have to lose this 4 electron or have to gain 4 electron. But it's very difficult to gain or lose 4 electrons. So what he decide? He decide to share his electron, right? He form bonds by sharing of electron. Form bond by sharing of electrons, and the bond that formed by sharing of electron called covalent bond. Covalent bond. Okay, now next thing is carbon has sp, sp2 and sp3 hybridization. Now you must be thinking that what is hybridization and why we need hybridization, right? Why we need hybridization? Because by hybridization we explain characteristics and geometry of polyatomic molecules. Okay, so that's why we need hybridization. Oh, let's take an example of CH4. Now, by simply see the electronic configuration of carbon, we thought that carbon has two unpaired electrons. We know that carbon has two unpaired electrons, and we thought that carbon should form two bonds with hydrogen and form CH2. But in reality, this is very unstable. And in reality, carbon forms CH4. It means carbon form 4 bond with hydrogen. So it must be that carbon have 4 unpaired electrons. So how we make 4 unpaired electrons? To make 4 unpaired electrons, this electron have to excite in p orbital, right? Now we get 4 unpaired electron, right? We get 4 unpaired electron, but now s and p orbital have energy difference. So for bonding, energy should be equivalent. So we have to vanish. We should vanish this energy difference. Of s and p orbitals. So to vanish this difference by hybridization, we intermix the s orbital, one s orbital and 3 p orbital. All right, 3 p orbital, and we get 4 sp3 orbitals. 4 sp3 orbitals. And these sp3 orbitals have equivalent energy. Okay, now these equivalent energies orbitals are called hybridized orbitals. All right, these have same energy levels. That's why we need hybridization, and the stability of these orbitals are very high. These orbitals are more stable. Why they are more stable? because in sp3 orbital, the electron repulsion tends to minimize, is minimum. Okay, that's why we need hybridization. Now you know that what is hybridization here. Hybridization is intermixing what we do here, intermixing of orbital of slightly different energies, orbital to redistribute it, right? Redistribute the energies and we get new set of orbitals having equivalent energies. All right, this is hybridization. Now we see that sp3 hybridization. Arrangement of sp3 orbitals. Now you know that s orbital is spherical in shape, okay? And p orbital is in the shape of dumbbell, right? And carbon have 3p orbital, 1s orbital and 3p orbital in sp3 hybridization, right? We already see this. And we have 4 unpaired electron and carbon bond with 4 hydrogens, right? And hydrogen only have s orbital, which is spherical in shape, okay? So hydrogen form bond with 3p orbitals and 1s orbital. All right, and the structure became like this. I tell you later what's the meaning of this wedge line, okay? This is tetrahedral structure. Now you get one thing, sp3 hybridization have tetrahedral geometry. Now similarly we see sp2 hybridization. In sp2 hybridization, carbon have 1s orbital and 2p orbital, right? And we get 3 sp2 orbitals of equivalent energies, right? As we see earlier in case of sp3. Now these three orbital have equivalent energy, right? Let's suppose an example of ethene. The double bond shows that one pi bond and one sigma bond. I explain this in later video. Sigma bond. Okay, now we have sp2, right? We want 1, 2 and 3 orbital, right? 2, 3. But this orbital cannot form bond with hydrogen. The two orbital 1s and 1p form bond with hydrogen, and this form bond with carbon, right? Sigma bond, and other form bond with carbon pi bond. Okay, now the geometry of sp2 is trigonal planar. Trigonal planar, okay? And the geometry of sp hybridization is linear. Okay, linear. And how we get sp hybridization? When we intermix one s orbital and one p orbital, right? And what we get? We get two orbital of s and sp and sp, right? We get two orbital. Now I hope you understand the hybridization part. Now one point is here to remember is that what's the difference between sp3, sp2 and sp hybridization. Now you can see that the percentage of S character is different in this hybridization. Like in sp hybridization, we have S character 50% and P character is also 50%. In sp2 hybridization, we have 33.33% of S character and 66.66% of P character. And in sp3, we have 25% of S character and 75% of P character. What this mean? Actually, S orbital, you know that S orbital is close to nucleus, right? S orbital is close to nucleus. So nucleus pull S orbital tightly as compared to p orbital. Now here we can connect electronegativity with this concept. Electronegativity is what? Electronegativity is the property to pull electron towards itself. So more the S character, more the electronegativity. All right. Now the order of electronegativity in sp3, sp2, sp hybridization is sp2 and sp3, right? Now, what is sp, sp2 and sp3 hybridization? How we can differentiate them by just seeing the compound? Let's see some example. Let's suppose we have CH3 C double bond O. All right. Now you see that carbon have CH3 CH2, then C, then O. Carbon form only two bonds, right? This means this carbon have sp hybridization. This carbon form bond with two hydrogens and one carbon. That means it has sp2 hybridization. Let's see one more example, like CH3 whole twice and CO. Let's open this structure in simple way. Oxygen form two bonds with carbon. Now this hydrogen A form four sigma bond. That means it has sp3 hybridization. Similarly, it also have sp3 hybridization, but this carbon form 1, 2, 3, 3 sigma bond, right? It means it have sp2 hybridization. Actually, if carbon form double bond, it shows that one bond is sigma and second is pi bond. Okay, and if carbon form triple bond like this shows that carbon form one sigma bond and two pi bonds. Okay, sigma bond and two pi bonds. Sigma bond always one. Compound can form only one sigma bond and two pi bonds maximum. Okay, now let's see structure of some, like how we can represent of structures, right? and we see how we represent sigma and pi bonding. As I told you before that sigma bond is spherical in shape, right? Spherical in shape, and when S and S orbital intermix form bonding, then they form sigma bond. So sigma bond is formed when two S orbitals form bonding. Okay, now and S always form sigma bond. Now for pi bond we have S P bonding, okay, P bonding, all right. By sidewise overlap, they form pi bonding, and bond that formed by sidewise overlapping is pi bond, all right. And the head-on overlapping, by head-on overlapping, the bond formed SP overlap. All right. Now there is two case by which we can form sigma bond, but pi bond can formed by sidewise overlapping, right? When s orbital is connected with p orbital by head-on, they form single bond, and the bond formed is sigma bond. Okay, when the when two p orbital is connect with when two orbital intermix by sidewise overlapping, right? As sidewise overlapping, they form pi bond. All right. Now count how many sigma and pi in these compounds. Let's see, we have hydrogen, carbon, hydrogen, and hydrogen. Now count the sigma and pi. 1 sigma, 1 sigma. These are sigma bonding. 1, 2, 3, 4, 5. All right. 5 sigma bond and 1 pi bond. Now take one more example. Let's suppose we have ethane. So we have 1, 2 pi bond, and how many sigma bond? 1, 2, 3 sigma bond. All right, I hope you get the point. Now we see rotation along sigma and pi bonds. As I show you that sigma bond is formed by head-on overlapping, right? Head-on overlapping. S or SP. S or P or PP. P and P, right? So we can say that the rotation along the sigma bond is allowed because we can rotate the molecule along the principal axis. Let's suppose this is p orbital. If they intermix by head-on overlapping, we can rotate the bond along the axis, right? Because the electron density, this is node where the electron density is approximately zero, right? Approx zero. And this is the lobes where the electron density are maximum. So the electron density present along the axis parallel to the axis, right? So we can easily rotate the axis. Similarly in this case and similarly in this case. But rotation in pi orbitals, pi bonds. Like as we told you before that pi bond is formed by head-on by sidewise overlapping, right? When these orbital connect with sidewise, they form pi bonding, right? Like this. Sidewise overlapping. And by sidewise overlapping, pi bond is formed. Now you can see that the electron density along the principal axis is zero, right? These are nodes. These are nodes, right? Now the electron density is maximum in these loops, right? So if we rotate the bond, if we like this, if we rotate the bond, the electron where the density is maximum, this should be break. If we rotate the bond, the electron density disturbed. So the rotation is sorry. So the rotation is restricted. In case of pi bonds, okay? Now, we have four types by which we can represent the structure. First is controlled structure. The control structure is the structure in which we can control the representation. Like in simple structure, we can represent carbon and hydrogen bond, right? Like this structure, we have 6 hydrogen and 2 carbons, right? 6 hydrogen and 2 carbon. This is the simple representation. Simple representation, and in controlled representation, we short up our representation. Okay, we short up our representation. Now, how we can represent this structure in controlled form? CH3, CH3. All right. Similarly, if we have this representation in simple way, we represent this structure in controlled structure like CH2 and CH2. I hope you understand the point. Take one more example, like we have CH3, CH2, 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 and then CH3. Now, how we can represent this structure? We see that CH2, CH2, CH2 is repeating unit 3 times, right? So we write this structure like CH3, CH2 repeats 3 times and then CH3. We short up our representation, right? Now the next way to represent the structure is bond line structure. Bond line structure. In bond line structure, we only represent the structure by line. Okay, like this. And these junctions represent the carbon. All right, these junctions represents the carbon. And how we can represent our hydrogen? We cannot represent carbon and hydrogen in bond line form. We see that if carbon is present in the junction, so the valency of carbon is for carbon form 4 bonds. One bond is already formed with this carbon, so the 3 hydrogen must be present in this carbon, right? So we can represent like this if this is branched structure, right? CH3 carbon with 1 hydrogen, because it formed 3 bond already with this carbon, right? And if we have any other elements other than hydrogen or carbon, we represent that elements. We represent another element except carbon and hydrogen. All right, now the bond, how can we represent double bond structure in this bond line structure? Like this. If we have 3 triple bonds, then we represent like this, all right, or this, all right. Now, next representation is bicyclic compounds. Bicyclic compounds. In this, we represent the cyclic structure like this. We represent the cyclic structure rings in bicyclic representation, and these junctions represent the carbon and hydrogen. We can see by valency of carbon, right? Let's see, we have carbon here and 2 bonds are already formed, so this carbon have 2 hydrogens, right? Now, next representation is very important, and the represent is 3D representation. 3D representation, right? Now, in this representation, we represent carbon structure like this. Now, you must be thinking that what is this dark line represents and what this dotted line represent. In this 3D representation, this dark line is called wedge, right? Wedge. And this dotted line is represent dash, right? And this dotted line represent that this hydrogen is behind, away from the observer. This hydrogen is away from observer. And this dark line represents the hydrogen that is toward the observer, towards the observer. All right, the tetrahedral structure like that. Two hydrogen are in plane. Let's suppose these are 2 hydrogen that are in plane, and these 2 hydrogen are first is towards the observer, that is wedge line, and this is away from the observer, this is dash line. For me, this is the away from the observer, so for me this is my dash line and this is my dark line. All right, now next thing is classification of organic compounds. Classification of organic compounds. Now we can see this classification by a beautiful chart. All right, let's suppose we have organic compound here, and organic compound is classified into 2 parts. First is aliphatic compounds, and second is aromatic. All right. Now I will explain this broadly with a chart like aliphatic and cyclic compound. Okay. Yes, these aliphatic compounds are no rings. These have straight chain or branched chain. All right. In this cyclic compound, they have closed ring structure like this, like this, like this. All right. These all are cyclic compounds. Now, cyclic compounds are also categorized into two parts, homocyclic and heterocyclic. Homocyclic and heterocyclic. In homocyclic, there is only carbon and hydrogen. Only hydrogen and carbon is present in the ring. Most important thing is in the ring, right? Let's suppose we have this structure, right? And one is like this. Yes, these are homocyclic. This homocyclic. This is also homocyclic because that element is not present in the ring. But this is not homocyclic because the oxygen is present in the ring, right? This is not homocyclic. I hope you get the point. Now, heterocyclic compounds are the compounds in which we have compound other than carbon and hydrogen in the ring, right? Like this, it also have other than carbon and hydrogen in the ring, like this, and one more example like this. These are the example of heterocyclic compound. Now, heterocyclic compound and homocyclic compound. Homocyclic compounds are also categorized in two categories like allylic, alicyclic, and aromatic. In alicyclic, they are non-aromatic. They only have carbon containing rings, right? Like this. No other element other than carbon, right? All elements in the ring are carbon, right? But in this, we have aromatic. Aromatic is, you can say that The aromatic is formed, is come from aroma. They have fragrance. Fragrance, okay? They are benzenoid or non-benzenoid. I will explain this with examples in next video, okay? And non-benzenoid. Now I hope you understand the chart. The organic compounds are classified into two parts, aliphatic and cyclic compound. Aliphatics are which are in straight chain or branched chain, no closed ring, no rings is present, and cyclic compounds in which ring is present. Okay, cyclic compound are categorized into two parts, homocyclic and heterocyclic, right? Homocyclics are those compound in which we have only carbon and hydrogen, right? Only carbon and hydrogen. Heterocyclic are that compound in which we have other than carbon and hydrogen element present in the ring, right? In the ring. Now, homocyclic is also classified into two parts, aromatic and alicyclic, right? Aromatic and non-aromatic, or we can say alicyclic. In alicyclic, we only have carbon and hydrogen like this. All right. In aromatic, we have benzenoid and non-benzenoid. This benzenoid and non-benzenoid I will explain in next video. I hope you understand the whole topic. In our next video, we talk about nomenclature, very important. So till then, bye bye, happy learning.